All right, so the first latent class that we're going to do is a very simple latent class. We have some data, and as we do this, after we run each one, I'm going to walk you through the things that we're looking for as far as testing the latent class, and how to determine the number of classes that we should have, the power to detect latent classes, and so on. And what each of these indicators mean when we go to report our latent classes. I also, in the module for readings this week, there are two papers, one that just talks generally about latent classes and latent profile analysis. One that I think is a very nice paper that has like 10 frequently asked questions about latent class analysis. And then I also put up two papers that I have done using latent class analysis. One that's published, and one that we just got a really, maybe the easiest revise and resubmit I've ever seen. It's actually kind of frustrating because I read through the reviewer comments and they're like, oh, you take too long. I'm sorry, I'm recording this. You take too long in the paper to start talking about like alcohol expectancies, and you spend too much time talking about latent class analysis. This is the first comment of the paper, and I'm just gonna, just for the heck of it, oh shoot. Okay, it's still recording. I'm just gonna pull this up actually and show it to you guys so you can see how long it takes me to get into this. I hope the reviewer watches my YouTube page. So the first comment is, he says, generally, you take too long before you start talking about alcohol expectancies. You waste time initially, you waste too much time in the paper initially talking about alcohol problems in college students, and you spend too much time talking about latent class analysis and not enough time talking about alcohol expectancies. This has nothing to do with what we're doing today. This is just me complaining to you guys a little bit. So let's talk about the first thing. They're right in the abstract. I actually don't mention alcohol expectancies very much at all. In fact, not until down here. So they're right about that in the abstract. But in the paper, let's look at the paper here. I do, the first paragraph, I say, here's the problem. Here's the problem with college student drinking, right? It's still an issue. And then I immediately talk about alcohol expectancies. It is the second paragraph. And they said I don't spend enough time on alcohol expectancies. I just want to point this out. There is one paragraph on alcohol expectancies. There is 2, 3, 4, 5, 6 paragraphs on alcohol expectancies. And they said I don't talk about it enough. Just, it gets worse. I spend too much time talking about latent class analysis, okay? So here's where I start talking about latent class analysis. I have this brief overview that says, like, previous research on alcohol expectancies has examined blah, blah, blah. However, more recent research on drinking classes has indicated consumption is only one aspect. So this is tying alcohol expectancies to classes, right? And guess what? I'm going to talk about drinking classes for one paragraph. One paragraph, and they said I talk about it way too much. Anyway, it drives me crazy when reviewers say stuff that is like completely the opposite of the paper, because how do I address that? Like, I don't want to go back and say, like, actually, everything you said is the exact opposite of what the paper is. But it is. So I think what I'm going to do is just leave it as it is and say, yeah, we've now put alcohol, we now talk about expectancies right off the bat, and we spend 6 paragraphs talking about it, and we only talk about latent classes using in one paragraph. Because that's actually all I really did, right? Okay, so that was me complaining. Let's get back to what we're talking about today. And by the way, well, I'll leave this open because I'm going to flip back over to it. Anyway, still recording. When you go to estimate a latent class model, let's talk about the input here before we move on to anything else. If it's latent class, we know that we have categorical indicators. And then in this case, our categorical indicators are U1 through U4. This is an example straight out of the M+ handbook. And have we looked, have I shown you guys the pieces of M+, the M+ handbook, and all of the stuff that you can find there before? Have we not looked at this? Let's look at this quick, because this is important, actually. So M+ is statmodel.com. M+ has this fantastic handbook. Where is it? Where's the M+ user guide? Why do I not see it? Here it is, M+ user's guide. So here's the user guide, okay? And in their user guide, they break down all of these different types of things. And so, for example, we have mixture modeling with cross-sectional data. If we click on this, here is the user guide for doing mixture modeling. And they draw the models out. They give you code for doing each one of these, which is very, very nice. It's fantastic. Even better, though, is if you say view examples, it gives you all of these different examples, the data for the examples right here, the code for the examples, the output for the examples, and a Monte Carlo simulation in case you wanted to do a similar example and needed to calculate power for it, right? I should have shown you guys this when we were doing power analysis, but down here we have Monte Carlo simulation studies. Here are all the different, or a number of different types of studies that you may or may not do, and you can download the Monte Carlo to calculate power there. Basically, every single one of these, examples of special features, you have, they give you input and data or a Monte Carlo input in order to simulate whatever you want to simulate. So it's an awesome resource. It's free. It's out there. I mean, anybody can access it, but you need to have M+ in order to run it, right? Of course, run the things. But basically, if you're working on your thesis or you're working on your dissertation, you can find the type of model that you are planning to do and download the Monte Carlo input, put in your numbers, tweak it a little bit so that it matches your model, because it's going to be invariably a little bit different, and then just hit run, and you've run a Monte Carlo simulation. Super easy to do, extremely helpful resource. So anyway, that's where the data comes from this first one that we're going to run. So if you're going to do a Monte Carlo simulation, or I mean an analysis, a latent class analysis, you only have to specify a few different things. You can specify, you have to specify use variables like we always do. And in this case, we're just going to use U1 through U4. In M+, U is a variable that indicates it's dichotomous. That's just the way that M+ codes things from their standpoint. You can code it however you want. It doesn't have to be a U. But M+, just for your knowledge, if you download one of their things, if the variable starts with U, that means it's dichotomous. If the variable starts with X, that means it's continuous. We're only going to use the dichotomous variables. The next thing that you need to do is specify the number of classes. You can, as we do this, as you do a latent class analysis, you're going to iteratively add classes, because we're going to say, like, okay, we're going to see if two classes are better than one class, and then if so, we're going to see if three classes are better than two, and if so, we're going to see if four classes are better than three, and so on and so forth. In the M+ manual and in the M+ listserv, and they publish all of their listservs out there. Like if you Google any question that you might have. So for example, there are great discussion boards. So if we say M+, LCA, BLRT, you'll get this, M+ discussion. And so there are these discussion boards where people will say, like, hey, I'm trying to do blah, 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 blah. If you do M+, let's see, I have posted in here a lot. Let's see if anything that I've posted has come up. There it says Rob Dvorak. Command F, Dvorak. First, let me apologize for my ignorance. That sounds like me, overly self-deprecating. And so there's actually tons of stuff from me in here. These are probably all things that I have posted in, and then some. Here's another one, local independence assumption. Let me see what this one was about. These are older things, right? I was wondering if there's a way to evaluate the condition number for the information matrix. Blah, 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 blah. I don't know about citations. So this is actually where I get a lot of stuff. Is there's like not a published study out there on this. And I ask Bengt and Linda or Timur, and they say like, well, there's no published study, but, and they just give me their opinion, right? And I'm like, I'm going to roll with that because they are very, very smart people. But anyway, almost any question that you have from M+ has been answered by one of the thousands of people that have posted questions, or it's been posted by one of the thousands of people and answered by one of those 3 people that run the site. And it is run by just like 3 folks. It's pretty impressive. But anyway, I also subscribe to their thing, and so I get constant emails about M+. Anytime somebody posts. So back to what we're talking about here. We're going to look at classes. As far as classes, you never have to put this. Why is that?
Because you're trying to start with 2 classes.
Yeah, you always have to, like, everything is in one class to start with, right? So the question is, are there more than one class? Is there more than just one group of people here, right? So we will start with 2, and we'll move on from there. We're going to specify that these are categorical. By specifying categorical, we're saying that this is a latent class analysis. If we just went like this, that's all that's required to change this from a latent class analysis to a latent profile analysis. In truth, there's only very minor differences between the two. The most major difference is one is using categorical indicators, which means when we go to plot it, it's a probability of being in a group rather than the most likely group means and group variances. So we'll get thresholds here instead of means and variances. Anyway, we're going to stick with this. Let's continue moving down. In the analysis command, you have to say that this is a mixture model. If you say, as long as you say mixture, M+ is going to try and figure out what the classes are. If you say mixture and you don't have classes listed up here, it won't run. You'll have an issue or an error. Next is estimator equals MLR. That is the default. If you don't specify MLR, then it won't work right. You can also say WLSMV because we have categorical indicators, right? And so you can use weighted least squares. In mixture modeling, the difference between MLR and WLSMV is extremely minimal. So it doesn't matter. We're going to stick with MLR for today, and we can run both and have a look. It doesn't matter. Starts. So this is an important point. You can say starts equals 0, and that means that it will just automatically identify classes on the first run of the model. This can be problematic because the idea is it's trying to mix together several models, which is why it's called a mixture model, mix together several random runs of a model to identify the most likely classes. Starts equals 0 almost always gives you a great model solution, but it's not necessarily an accurate model solution. I'm gonna show you what I mean here in a second. If you don't use starts equals 0, then M+ will automatically use 10 random starts. And of those 10 random starts, it will usually do between 3 and 5 of the best 10 mixtures that it finds, and it will give you a log likelihood. The idea is that that best log likelihood gets replicated at least once. So as long as you come up with the best log likelihood 2 times, then M+ is considered to have converged correctly. You will not get that replication if you put starts equals 0 because it doesn't do multiple mixtures, right? It just does the single one. You'll see what I mean here in a second. This is why I've got starts equals 110. 100 is probably excessive, though when you get to latent profile analysis, you might need 100 or even 500 starts with a whole bunch of last stage replications in order to make sure that you are able to replicate your this will make more sense in a second, but make sure that you're able to replicate your two lowest log likelihoods. Yeah.
So there should be one number there, or
No.
is there supposed to be two?
You could, if you put starts equals 0, then it will just run with that one number. If you put starts equals 1 and you don't put a second number, you'll have issues. So if you put any number other than 0 in there, you have to put a second number, because it's saying like, okay, we're going to have this many random starts and we're going to use this many final selections, right? So oftentimes I'll go 20 and 10 for those numbers. M plus, like I said, their default is 10 and 5. You can do whatever mixture number of numbers that you want, as long as the second number is less than the first number, because you can't select more random runs than what you're actually specifying.
So like the 10 is saying that it's going to provide us with 10.
The last 10, yeah, or the 10 best. I'm sorry, it's not the last 10, it's the 10 best, yeah. The next thing that I have there that's commented out is LRT starts. So when we do these models, there's a number of things that we use to decide whether or not the number of classes that we've selected is the most appropriate number of classes. It's difficult to say. I mean, sometimes you're going to get to a spot where it's nuanced whether you have 3 eggs or 4 eggs, right? And some indicators are going to say like, yeah, there's only 3 eggs, and some indicators are going to say, no, there's 4 eggs. And one of the most telling ways to determine whether or not we have 3 eggs or 4 eggs is through the Low-Mendel-Rubin likelihood ratio test, right? And this is a chi-square test. What is the problem with chi-square or z or f or t or any of that? Any test that's stuck in a table somewhere, there's a problem with those. What are the problems? What is the main problem? Why do we not use z-test to test indirect effects anymore? We used to use the Sobel test, right? Why don't we do that anymore? Yes, perfect. We assume that there is a very specific distribution, that our data follows a specific distribution. And for a long time, we had to make that assumption because there was no other way to do it, right? When we were first coming up with kind of basic inferential statistics, these tables were really important. They're less important now. Now we can use our distribution to calculate what our cutoffs should actually be. And so we have now a bootstrap likelihood ratio test that we can use. The bootstrap likelihood ratio test, though, it capitalizes on the fact that you're doing mixtures and running multiple models, right? And so you can include a whole bunch of these models as part of your likelihood ratio test. However, it winds up sometimes providing distributions that can be so excessive that everything will always tell you that the number of models is that higher number of models is better. So you have to take that with a grain of salt based on the straight likelihood ratio test. I'll be honest, I've only ever seen 2 outcomes with and I've done a lot of these models. I've only ever seen 2 outcomes. The first outcome is that it's statistically significant, which means we should just always select the model with the higher number of classes. And the second one is that it can't replicate the last log likelihood or the best log likelihood or any of the log likelihoods, and so you can't rely on that test. I've never actually seen it just say like, oh yeah, it converged fine, and there's this doesn't suggest that the higher number of classes is better. So it's one of the pieces of information that we use to determine if we should be selecting that class, but it's not the be-all and end-all, and sometimes it can be very problematic. If you search the M+ discussion boards, you'll find sections where Linda says, yeah, it's just like it's not going to work for you for this one, like disregard Tech 14. You get that by putting in Tech 14. Tech 11 gives you the Low-Mendel-Rubin and then just a plain likelihood ratio test. Low Mendel-Rubin is a corrected likelihood ratio test. All of this stuff probably makes very little sense, so why don't we run the model and walk through it a little bit, and we'll go from there. So we can't run this with class equals 1, so we're going to put class equals 2. We're going to hit save, and we are going to hit run. If you put starts equals 0, it will still run a few random starts because it's got to be able to pull the, I'll show you here. Oh. Yeah, so it ran 15 iterations here. And it will run a random number of iterations, but it won't have any random starts. And what I mean by that is the random starts are when it actually will take a step back and say, here's this log ratio, here's this log likelihood that was replicated, here's this log likelihood that was replicated, and those are within the random starts. We're not going to see that here. We're not going to see any type of replicated log likelihoods because we didn't specify any random starts. All right, so we scroll down. Here's our univariate proportions for each of our 4 items. And we're going to get some model fit statistics. You really only get one that we're normally used to seeing, and that is the chi-square test, right? So we have Pearson's chi-square, the likelihood ratio chi-square. They're going to be roughly similar. This is the one that I like to rely on. I'm not a fan of the Pearson chi-square test, though. It's maybe a little bit more robust to categorical variables. So it's up to you. The likelihood ratio conforms to like a Wald chi-squared, and I mean that's my preference is a Wald chi-squared. Probably be just because I understand Wald chi-squared a little bit more than I do Pearson chi-squared. But either way, here they're roughly the same. They're not significant. What does that tell us about our latent variable model? Ideally, it's a good fit to the data, right? Yeah. If we scroll down, we see that we have 2 latent classes. And here is like the rough proportions. And it will actually give you, if you scroll down, the exact proportions, 373, 127. Those are the final class counts. That's the number of people that the analysis set are in this one and the number of people in this one. So 75% and 25% in each class. Classification quality, this is entropy. Entropy is a value that indicates how clear the distinction is between the classes. And in this class, when it's between a simple 2-class model, entropy collapses to be roughly equivalent to Cohen's d. In here, Cohen's d would be then 0.9. This is not true as soon as you have 3 classes, but at 2 classes it is true. Research suggests that in order to correctly classify classes, you need a Cohen's d of 0.8 for 2 classes and an entropy of 0.8 for anything beyond 2 classes. That means at 2 classes it collapses still to 0.8, right? So the value that you want for entropy is 0.8 or greater, and that indicates, that's a strong indication of class discrimination, being able to tell the difference between 1 class, 2 class, 3 class. While we're on the topic of classes, actually, let's do this after the next one. So we also use AIC and BIC to determine if this is a good class value. So we have 1986 for our BIC here. Better classes are determined through lower BIC, but there's no way to formally test lower BIC, right? Although there is a great paper, it's not a great paper, there is a paper by a sociologist, oh gosh, what is his name? Starts with an R.
Raftery?
Yes, thank you. Who gives a table of what BIC values should be in order to conclude that they're significantly different. That table puts a p-value or a BIC difference of 10 as statistically significant difference. Man, that like you can get a value of 10 by doing almost nothing in a model, right? You can change that BIC. So I'm not a huge fan of it with latent variables. because BIC can change an awful lot with very small changes to your model. Small, what I would consider non-significant changes to your model. So, all right. Let's scroll down here. Entropy looks good though. We're above 0.8. Here we have our thresholds. And that is actually less important than the probabilities. The probabilities are what we are going to use to build our table or our figure for this analysis. We're not going to build it just yet. We're going to continue working to make sure that we have a correct model. Here are our LRT values. You can see that this is both for the low Mendel Rubin adjusted LRT and the likelihood ratio test, the non-adjusted. Two classes are better than one. There's at least two classes in this data set. Similarly, if we do a bootstrapped one, two classes are better than one. Our value here is 585. Our value here is 585. Like, these are very closely linked tests, right? Okay, let's go back. And now what we want to do is test a three-class model. Just FYI, if your classes exceed your items, M+ is going to give you issues, right? Because you need to have at least the same, you can't have more items than what you have. You can't have more classes than what you have items. It's basically, this is equivalent to factor analysis, right? If you have 4 classes, then what that would boil down to is 1 class per item. And in factor analysis, if you have 18 items, how many potential factors can you have? 18. You can't have 19, right? And latent class analysis works the exact same way. All right, so let's look at 3 classes. We hit run. It's going to do its thing. It's probably going to struggle a little bit here. And it again ran 50. So the reason that it did 15 iterations here is actually because I selected to get Tech 14. And if you do Tech 14, it's going to give you a minimum of 15 iterations, even if you have 0 starts. So, and that's because it has to try and compute that bootstrapped chi-square test. Okay, so for starters, we have a problem here involving parameter 2 in C2. And as we scroll down, our model actually seems to fit good. It looks like we have 3 classes. Whoa, something happened here, right? Entropy looks terrible. So it did give us 3 classes, but it's not very good at separating out those classes. We come down to our, not our thresholds, but our probabilities for each class. We can see that as we start getting here, like item 4 is not discriminating very well. Oh, it does for this class, though. I don't know. Those are our 3 classes. Then as we get down here, okay, so this test would suggest that we don't have 3 classes. Ooh, look at there. This test actually suggests that we don't have 3 classes. So I stand corrected. This is the first time I've seen this. I don't think I looked at this when I was doing this, but this is our bootstrap test, right? Here's our p-value. That would say, hey, 3 classes are not good. Our BIC before was what? Anybody remember?
I think 14 something, no?
I thought it was 19. I thought it was 1986. And this is 1953. So our BIC dropped by 33.
2012.
What? Oh, it was 2000. Oh, that's right. Our BIC increased.
Yeah, so it's definitely not.
Oh, it's definitely bad. Yeah, you want lower BICs. BIC increases here. So yeah, this is not as good of a model, right? There's some problems with this one. This is our stopping point. We can stop right here. We know entropy goes down. All of our likelihood ratio tests suggest that there's not 3 classes. BIC goes up. You will never see this good of evidence that there are that you are supposed to stop. If you read in the in the M plus things, Linda will say, as soon as the p-value for one of those likelihood ratio tests crosses the 0.05 threshold, you should stop. Reviewers will tell you otherwise. I can tell you that from experience. But I tend to try and rely, like many things in latent variable analysis, you're never going to have perfect data, right? Data is messy. That's especially in psychology. Yeah, you got a question, Aaron?
Yeah, so my numbers match up with yours pretty well, except for my entropy is 0.81.
Because same with me. Did you leave your random starts on?
Yeah.
Yeah. So
Ah.
same thing with me.
Yeah, so if we go back, then let's do that. Did you guys do starts?
Yeah.
110?
Yeah.
Okay, let's do that. This will take a little bit longer.
Oh, no, I didn't do that.
No.
Yours just said starts equals 0?
Yeah, oh, that was missing. I'm bad.
So let's run this. This will actually take a little bit to run. When it's doing this, it's running not just 100 mixtures, it's running 100 mixtures per class. So every time you add a class, it's adding 100 mixtures and then 10 more things at the end. And so it ran our 100 mixtures. Come down here, we still have some issues. But now we see something that we didn't see before, and this is best log likelihood value has been replicated. And you can see that it's been replicated every single time, right? Here's our final stage log likelihood. These are the seeds for those log likelihoods. So best log likelihood is replicated. We're good to go there. That still is the same. Our entropy has gone up to 0.81. That's a little bit better, right? It dropped dramatically from what it was before, but at least there's entropy now. I mean, at least it's within a reasonable limit. But our test here would suggest that that's not significant, that there are not 3 classes. And our BIC stays the same, right, to 2012. So I would conclude from this, we do not have 3 classes.
So just to make sure, whenever you do, basically when you do the test 14, it's going to compare the number of classes you have minus 1.
Yeah, so Tech 11 and Tech 14 do it. Tech 11 gives you the Low-Mendel-Rubin LRT test and the corrected Low-Mendel-Rubin LRT test. And then Tech 14 will give you the bootstrapped one. So Tech 11 gives you one, Tech 14 gives you the other. Occasionally Tech 14 just like won't converge, and then you just have to remove it and just go with Tech 11.
Had a situation where one said there was a significant difference and the other one didn't?
Yes. We'll see one of those here in a little bit.
Okay.
It's especially common when you have a lot of indicators and you're doing latent profile. You'll find that oftentimes the Low-Mendel-Rubin will say it is not significant, but the BLRT will say that it is. I've never seen it the opposite. I've never seen it where BLRT says it's not significant and Low-Mendel-Rubin says it is. Because BLRT is correcting your distribution or correcting your cutoffs based on the distribution of bootstrapped data, whereas the other one is following a chi-square table, right? And so the BLRT is always going to be more likely to give you a p-value less than 0.05. Which, on the one hand, it's nice because it's using your data to figure that out, right? On the other hand, that means it's less conservative. So you have to kind of go with. I mean, my preference actually, and people vary in their preferences. My preference is not to use the BLRT, but just to use the regular because it is more conservative. But I have a friend who will say, like, no, you should always use the BLRT. You should bootstrap everything that you possibly can, right? You should never use a distribution out of a table. I don't know.
So wouldn't the bootstrap one have higher power?
It does. You're right. No, you're absolutely right. It does have higher power. All right. So let's set two classes. Starts 100 and then 10. And just FYI, all right, not FYI yet. I will get back to FYI. So we can see our best log likelihood has been replicated. We have 10 here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And that's because we had 100 random starts followed by 10 draws for the log likelihood, right? And it says that you should rerun this with at least twice the random starts to check that your best log likelihood is still obtained. You can go back and do that if you want to. Chi-square looks good. You won't always get this chi-square, by the way, just FYI. And we'll talk about that in a little bit. Entropy looks good, 0.904, which is what we saw before. And this looks good, and this looks good. Where is it? There we go. Oh, look at there. Of the 5 bootstrap draws, 3 draws had both a smaller LRT value than the observed and not a replicated best log likelihood. So when you run into this, and this is the thing that I said I see all the time, I either see it significant or I see this. The way that we address that is to come back up and say, all right, we're going to do LRT starts, and we are going, these first 2 numbers are always 0. I don't remember why, to be honest. But I know that they are. And then we have 110, which should match our starts. You can actually put these numbers higher than your random starts. That's fine. This will run separately. It will take a little bit to run. Let's do this. Let's let it run. And while it's running, since this will probably take a while, it might or might not take a while. But yours is done already? Okay.
This computer's a fast.
Mine's still going. There we go. All right. Let's just scroll down here and look at this. So by doing that, we were able to pull 10 starts instead of the default, which is 5. And if you want, you can go and make that second. You can make that last number 100, right? And it will run this test 100 times. Trying to replicate the best log likelihood in there. But anyway, you can fix that test by simply changing that value. And in this, it would say, this suggests that we should run, or that we should run with 2 classes, right? All right, we're going to take a break. And when we come back, we are going to say what?
You said it suggests with this new line that we should have 2 classes.
Oh, so we ran 2 classes, and we compared that to 3 classes, right?
Oh, I thought you were looking at one.
Oh, so this down here is comparing it to 1 class, but we already ran 3 classes, and it said that 3 classes was not good, right? We hit a stopping value. Yeah. Okay, let's take a break.